Hello everyone, good evening. Welcome to another professional development meeting hosted by Institute of Internal Auditors Madras Chapter. Today with us we are having Mr. Ashok M, a very veteran data scientist with us to share his knowledge and experiences and correlating data science with internal audit profession. So I'm briefly giving the profile of Mr. Ashok. So Ashok is an experienced data scientist and a finance professional. He has significant teaching experience in teaching Python, statistics, machine learning with leading data science training institutions. He has his deep expertise in finance domain. He has worked with leading research organizations and financial advisors. He is also a consultant for providing financial data analytics. He is currently guest faculty at the Great Lakes Institute of Management, Christ University School of Business and Management, Bangalore, the Institute of Chartered Accountants of India, Institute of Cost Accountants of India, and EduCity. He is also a trainer in LearnBase, XLR Solutions, Skill/Academy, and he is also co-founder for CAP Advisors. He is also a chartered accountant, registered valuer, CFA, and he has a lot of licenses and certifications in the domain of data science. I hope I conveyed in your profile in a precise manner, sir. We are looking forward to be enriched with your experiences. Thank you very much for joining us today. I'm handing over the session to you. Thank you very much.
Thanks, Deepika. That your introduction was fine. Covered most of it of what I have done. So, without much ado, let's dive into data science. Data science, as in, I think it makes sense if I just step back a little bit and share my experience before just starting off what is data science, etc. How I started with data science, what was the necessity. So data and analytics and analysis is something that we all do, as many of you might be chartered accountants. We all do at our day job, whatever that profession is, whatever specific focus is. I was in the domain of investment analysis, so portfolio analysis, etc., and optimizing the best set of stocks and bonds was something that that we do a lot in when we advise institutions and clients. So it all started with basic Excel. Yeah. So it all started with basic Excel tool analysis, but then as the employer becomes more demanding, as the situation becomes more demanding, start exploring other tools. So in that journey, I started using statistical tools like MATLAB, SPSS, etc. So the whole idea of optimizing returns, optimization is nothing but you have finite resources, there are constraints, and then you have to maximize returns for the client. So this problem solution can be extended into any domain. It's not necessary that it has to be only in portfolio management. So one thing led to another, and you start moving up the value chain and see that there is this whole field called data science, which has more set of tools. And as I explored more, things were not obviously in a straight line. You just don't become a data scientist overnight. I don't think anybody of my era at least became data scientist. So you digress, and then you learn a little bit of coding, and then it goes into other things like automation and all that. And then finally, you come back to data analytics, because that field has taken off in so many different directions that there are a lot of tools, a lot of advancements in terms of algorithms, and then it becomes very interesting, and then it extends beyond finance. And in fact, I am, as Deepika has introduced, I am a trainer at a couple of places, and most of the training has very little to do with finance. The field of data science largely applies outside finance and investment management, at least, is something that is lagging behind when it comes to application of data science and all these tools. So things are changing slowly, and some institutes like the CFA Institute, of which I am a member, they've started introducing data science in the curriculum. Okay, so introduce data science in place of something else. So some old stuff we stop learning and we start learning new things. This is, but then the question is, it's just not that we do data science in only in certain segments. We eventually want to use it in finance. And I was approached for this internal audit. How do we use an internal audit? And frankly, it's not something that I can easily look up the internet or speak to someone who has used data science in internal audit. I literally had to go back to the basics. What is data science? So even though I've been teaching for the last 3 years, I've taught close to 300, 400 students probably. When it comes back to our profession of original, the mothership, which is the CA profession, and then start thinking, okay, how does it apply to accounting and financial statements? It becomes very challenging because the amount of work that is done, at least the public research, it's significantly lacking. That's something that we need to solve together. It's not that I'm a data scientist guy and you are a CA, and then the, we need to make the threads meet, and we need to solve this thing. How do we apply data science? So your involvement in this session is as much important as my own thinking, running my own brain cells and figuring out where will data science. So it's not so much like you ask me, hey, tell me where data science is useful. It's about me telling you what is data science, and you taking your domain knowledge and bringing it together, and we both work out what is possible what is at least what are the low hanging fruits that we can take from this field. Okay, so I want to give a background in the sense that it should make sense that why a CA guy is in data science. And I'm optimistic that eventually, like I said, the CFA curriculum, hedge funds, especially with the new things like generative AI, it's significantly started penetrating into the domain of finance. But otherwise, the historically data science has been in other fields like banking, retail, and other data related, not essentially to solve any particular financial problem, but more to analyze customer segments, churn, customer retention, and things like that. So it's been used in a narrow domain, but now we'll understand what is data science, and we'll see if it's possible to extend to your domains. So this session, the session is not about jargons and things like that. You really need to know what is data science without any frills. It is not about using very complex jargons like generative AI and all that. It's really goes to the basics, 101 principles of what is data science and how it can, and then we will come to what are the potential areas where you can extend this. Okay, so, okay. So, so what has been the purpose of AI? Purpose of data science. So, data science is a subject. Okay, it's a collection of tools and techniques. So it is actually a cross-disciplinary field. Okay, it's a collection of tools and techniques. So these tools and techniques are essentially, you can say, it's a mix of computers, softwares, algorithms, logic, math, all this put together. It's a multidisciplinary tool that that is used somewhere. Okay, so where exactly it's used is that we are trying to create or extract value from data. Okay, so you have data. So you have data, and then you're saying that there are some patterns. There are some patterns or relationships. Okay, there are some patterns or relationships that are hidden in mountains of data. Okay, so this is a backward looking exercise in fact, that you take historical data and you parse through the data, and then you find that there are some unique relationships, and one thing is pointing to another. Okay, so what is that relationship, and then how can we manipulate those variables in order to maximize something. Okay, so it's like in accounting sense, it's like if you increase price, the sales volume decreases, but we say the dollar revenue might increase. If costs go up, uh, profits go down. So those kind of relationships, some of those relationships are very well known, but a lot of other relationships are not easy for the naked eye. It's not easily understood. So why suddenly we are looking at data is because data has exploded in the last few years. It's become easy to gather data uh, because of internet, because of purchases that people make online. You leave your data print in a lot of places like banks, government repositories, and so on and so forth. So there is a lot of data that's available, and the question is, now how do we use this data with a set of tools and techniques, and then you unearth certain patterns. Okay, so you go from X to Y. I'll come back. We'll come to what is this X to Y, etc. We're looking for some patterns. So, firstly, data science has been used by organizations quite successfully. Uh, Probably the biggest example is Amazon, Google, Netflix. These are the organizations that have successfully mined data. Uh, they have mined data to find out very um, profitable opportunities to exploit. So it's always been about business. The business has driven the field of data science. So, for example, there are some KPI measures like ROI, market share, or customer retention. How many customers have you retained at the end of the year? Sales growth, customer satisfaction. So all these are the output. Okay, output. These are the results. Okay, these are the results that we want. We want a high ROI. We want a high market share. Businesses want a high retention rate, high sales growth, high customer satisfaction. But there are a number of factors that sort of drive this result. Okay, the number of factors that drive this results, and people are very open to uh, figuring out what those factors are. Okay? There are no rigid rules that, okay, in accounting it says that so this is the formula for ROI. I need to maximize this. In data science, we are pretty open to putting any sort of relationship as long as we get some mathematically backed result that something is maximizing something else or something is driving something. Okay, so these factors leading to these results is something that companies started digging deeper because there was more data. Okay, and then you use all the principles of data science, and you figure out those factors, and then you focus on those specific factors. Which among 100 factors, maybe the top there are 4 factors that drive significantly ROI, okay, or customer retention. So what are those factors? What is the weight attached to each factor, and how do you maximize those weights? So in the case of Amazon, they have run this profitably. Similarly, like I said, Google, Netflix. Netflix is one of the important drivers of the field of data science. Okay, so the company Netflix has had a huge impact. So this a bit of history. This is like don't remember the exact year, maybe 2008 or something, when they announced a challenge. I think it was $1 million challenge. Okay, they announced a $1 million challenge what they did is they just provided data free of cost to people, to the public. Okay, what data? Data about what you and I watch on Netflix. So several million rows of data. What is which geography we are from, what is the preference, how many movies we watched, what genre, all these data, how many hours you watched, etc., was made into a file, and they gave it to the public for analyzing and coming back and telling Netflix that what is the significant driver in this thing, so that Netflix could tailor shows and bring on better programs.
Hey, what happened? Where are you?
Okay, so yeah, please go on, Narayana. Somebody raise the hand. Okay. So Netflix came out with this competition. So it was a competition to win $1 million. Somebody who can figure out the patterns in the data set. Okay, patterns in, basically it's all about users and what movies they watched. And you need the person who solves this essentially need to come out with an algorithm that will easily tell what is a user's preferred movies that he watches. Like for example, when you open your Netflix login, you log in through Netflix ID, you say you see a set of movies. I see something else. I see a different set of content. So that is an algorithm which is tailored based on our user prior history. So, so that's when a lot of algorithms were developed, and some, I think AT&T, Bell Labs, or some team had won this. And at that point of time, there were no ready-made machine learning algorithms available. So this team wrote those software from scratch, and they won this prize. So this kind of sort of triggered the imagination of several other people, and everybody started working in this direction. And then you saw an explosion in data science or machine learning algorithms. We'll come to what are machine learning algorithms, etc. So, so understand the association between KPIs and the factors that have a significant effect on the KPIs for effective management. Okay, so management wants to know how to maximize, achieve certain KPIs and what factors drive them, and they are willing to throw any sort of tools, techniques, which we now call as data science. Okay, so it's in order to maximize the KPI. So identify the critical factors that positively, negatively affect KPI and take appropriate action to optimize performance, allocate resources, and create value for the organizations. So this is one major perspective of data science. And today, actually, it's been used for several other research purposes, etc. But largely the field of data science is a multidisciplinary field, came together to solve business problems. Okay, so I'll just give you a preview of some names, some algorithms, okay, which are used in data science. But I promise I'll come back to this at a later point. But just look at these. Basically, there are algorithms. Algorithms. What is an algorithm? Algorithm is nothing but a sequence of steps, right? Sequence of steps or a method of doing something. Okay, it's like a recipe. Okay, so a chef has a recipe how to make a dish. There are 10 steps of doing making a dish. So that is an algorithm. There are different types of algorithms. So the algorithms based on its logic and math involved in it. We have a set of algorithms. Okay, there are like thousands of algorithms. This very famous book, which has all the computers, most of the computer students, computer science students study that. In data science, we have probably some 100 algorithms, but the most frequently used one are about 25-30 algorithms. Okay. So what is an algorithm? An algorithm is just it's a skeleton structure. It's a mathematical formula, you could say, that gives you a particular solution. Okay, from factor to result. Okay, from X to Y. That is called as an algorithm. Okay, so we do all this in a very deterministic way, in the sense these algorithms are very clearly laid out. Okay, there's no. It's not like it will run differently if you if you run it twice, it will give a different result. Sometimes it gives because of certain other random number sequence, but by and large, the algorithms are stable. Okay, so you have something called as decision trees. Okay, you know what a tree is. So I think some of you would have studied at least in your CA option valuation. You remember? Anybody remembers binary option valuation? There is a tree, right? So things go like this. There's a decision, and then price can go this way, up, down, and once it goes up, then again it can go up, down. So here also in data science also we have something called as a decision tree. This decision tree is can be used in several ways. One application is to find out factors that influence sales growth. Okay, so factors that influence sales growth. So basically, you want to know at what sales growth. Let's say if you want to achieve sales growth between 10 to 12%, what factors are required, or combination of factors that achieve this 10 to 12% sales growth. Price, what is the margin, how many employees are required, how many machine or labor hours. Okay. So you could get to certain results like particular sales growth level, etc., through decision tree. Just you just look at it at a basic level. Don't worry too much about what is decision tree. We'll come back to a few of these things at a later point. Then there are something called as associative rule mining techniques. Okay, it's another algorithm. It basically looks at customer purchase behavior. Okay, something like your Netflix example, or something that you buy on Amazon. You tend to buy certain products. Okay, so a student will tend to buy books. A housewife might tend to buy household items for the home cleaning stuff, etc. You look at users and you look into what is there inside their shopping basket. This set of algorithms, by the name association rule, means if you buy, let's say, milk, then you necessarily buy bread. Okay, so this is one obvious, or maybe you have egg, milk, bread as one basket. Okay. So this is a one set of techniques. What products are chained together? Which are 4 products going together? 5 products become a basket. Like fruits, some set of fruits and vegetables will become. Okay. Then we have something called as clustering algorithm. Okay, clustering means together. Okay, coming together. Like T Nagar is a cluster. Okay, or JP Nagar is a cluster. Okay, so in that sense, a set of customers could behave similarly. Okay, cluster. Okay, so tier 1 city customers could become a cluster. Okay, a particular income level, above a particular income level, could become a cluster. So these are all algorithms. Okay, these are all algorithms, these are all math-based algorithms, softwares which are packaged together, which needs to be used in the right place for the right problem set. Okay, and then you have this linear regression. So it's a very familiar one to most of us, at least what we studied in school, linear equations. So it's similar. It's actually a linear equation. Linear regression is a straight line. Okay, so it's a straight line. So you could put some relationship here and like for example, a number of rooms and price. So it's a housing data set. You have 1, 2, 3, 4 rooms, and the price goes up. Okay, so you could use for straight line relationships this algorithm called linear regression. Somebody is raising hand. You can ask question.
Yeah. Hi, Narayan here. Can I ask?
Yeah, sure, please.
Okay, thanks for that. Just a quick question. Like, so when you talk of these algorithms, so as a practicing, internal auditor, would it help to have a deeper understanding of the statistical rule-based approach, or a mere, say, understand a problem definition and then understanding the approach, and then I take technical help? Would I require?
Yeah.
Would I be required to deep dive into this statistical approach? That's my question.
Yeah. So to know the statistics is just good to know actually. But if you know which machine learning algorithm to use where, that's more than sufficient to start implementing these machine learning algorithms. Okay, so how decision tree works is something that a full-time data scientist would be engaged in. Okay, so what is a cost function? Which how to interpret certain results from the decision tree? Which decision tree is better? When it comes to those, then yes, the math involved might give you a deeper appreciation. But then if you are implementing it and you want to start implementing machine learning algorithms, just a basic idea of statistics would.
Okay, thank you. Thanks.
Okay, so we also hear about various terminologies. So the thing with all this developments is that the terminologies are very, it is what puts us off. Okay, there are too many terms floating around. The latest one being generative AI. Everybody's talking about AI. Many people are talking about generative AI. And then there are also other terms. Okay, data science itself is one term. Then there is AI, there is machine learning. There is also something called as deep learning, and so on. Okay, so what is data science? I think it should be kind of you will have a sense now. I've said that I've told it's a multidisciplinary approach. It's a set of tools and techniques to solve business problems, to look for patterns in data. Okay, it's all historical data. There's nothing that the computer can do without data. Okay, so the profit is in the data set. It's not just data, it's in the relationship between the variables that you need to mine and figure out. Okay, through various algorithms. Those algorithms are going to help you in determining those relationships. Okay, so that is data science. And the question is now, then what is artificial intelligence? What is AI? And this slide, I think you guys could just jump in and tell what you understand by AI. Anybody could go. Is AI and machine learning the same thing?
Hello, Deepak here. I think AI mimics human thinking, and that involves vision, that involves understanding language, and of course, it involves in taking decisions using reason. So AI includes machine learning because it includes reasoning, ability to reason, and also you also need sensors, so you need sight. So AI also includes that part of what do you call like computer vision. then also you need to understand the language. So AI includes these aspects also, apart from reasoning.
Okay. Great. That's a good answer. Anyone else with a different perspective?
Sir, this is Sridhar.
Yes,
Sir, we see I see this AL, ML, and deep learning are into each other, where it automatically understands the standard set of patterns that at least once seen by the system, it automatically adopts and start performing. AI is on the higher side as a mechanism, we can say, is what I understand, where the machine learning to some extent certain sets it will perform the task, and deep learning is on one aspect certain repeated scenarios. Once it sees more than 2 instances, it captures as an instant and start applying and gives out an output, is what a little I understand.
Yeah, I'm with you on the AI and ML part. I'll clarify what is deep learning. I think there's some difference in what I want to say in that aspect. But I think you are spot on AI and ML. So the way I look at it, and the way things have evolved is AI is actually a very old terminology. Okay, the first time it was used was somewhere in 48 or something. Okay, I forgot to take the exact reference. But 1948, 49 is when the terminology of artificial intelligence. Soon after the modern computers were invented, the term of AI, that AI was also being talked about much in the similar way that we talk today. So the 50s and 60s, there was a big rage about artificial intelligence. And as Mr. Deepak said, it's exhibiting human-like intelligence. Okay. So they looked at computers as doing anything that humans did or what helped human beings. So do calculations, take images, process images, take dictations, send a letter, send an email, basically communication. So anything that assess humans and or did what humans did. Okay, so you could say a computer is an artificial intelligence in that sense. So it's a continuum, it's a spectrum. Okay, so it starts in a very rudimentary calculator, and then it goes all the way, and there is somewhere where it would reach human potential. Okay, and after that it will become superhuman. Okay, that at least that is the prediction. Okay, that it will overtake humans. Okay, we are somewhere, probably somewhere here. We don't know. So where human when this gap, okay, when this gap will be bridged between what currently computers can do and when it will overtake humans is something that people are debating. So I think you would have heard prominent voices like Elon Musk, Sam Altman, Ray Kurzweil. So there are some prominent voices out there who say, or put a date to this. For example, there is this great author, sci-fi author called Ray Kurzweil, who has put a date of some 2045 or something. Okay, and he's writing a book now. The title of the book is, it's much nearer. AI is nearer. Okay, so he wrote a book called AI is Near, and now he's writing a book called AI is Nearer. So that means it's less than 2045. Some people think it might take 200 years. Okay, some people think it might never happen. So that it's an open debate. And then what happens beyond this? Okay, what happens when you reach human intelligence level and then you exceed? AI exceeds human intelligence. There is again a debate on the ethical aspects, whether it is good or bad. Okay, so there are some in the camp like Elon Musk and Yuval Harari, if you read this book. So these people are negative. That is, they want government to impose restrictions on AI reaching this human potential, because they think that once it reaches human potential, AI might overtake human beings. Okay, AI might harm human beings. Okay, it might take over the world and bad things will happen, or bad people will use AI to hurt others. So basically, Elon Musk is in the camp of saying that it's a bad situation to be in. Whereas there are others who are positive. Sam Altman is positive about, and few others are positive about this thing, saying that you will have abundance. Okay, so basic economics is that we always live in scarcity, but if AI overtakes human potential, it will solve the problem of scarcity. So it is both a plus and a minus debate that is going on currently. Okay, these are all slight digressions, but anyway, I thought if you are interested, you could go and research. But there is a name for this point. Anybody knows what is this this point in time? What is this event called? What is this called? From science fiction, it's not like it's a mathematical term or anything. We call this by a term. Sorry?
0 day.
Zero. No, not zero. No, but somewhat similar, somewhat close. Okay, so this place, when it will reach human potential, they call it a singularity. Yeah. So singularity, it's just a borrowed terminology. It's not an original term. They're just using it to say that what happens after singularity, we don't know. Okay, it's a term to say that what happens when machines overtake humans is a world which we cannot predict. Okay, this term is borrowed from the Big Bang theory. Okay, so basically there was nothing, and then there was a huge explosion. Okay, this I'm talking about 14 billion years ago. There was nothing. Okay, basically no space time, and then there was a huge rapid explosion and inflation. Okay, and then all planets and everything started evolving. There was space time, concept of space time. So this event is called a singularity. Okay, so they're just borrowing that phrase to say that the current what we know is not sufficient to predict what happens after machine state. Okay, so all this is bordering on fiction and science fiction and all that. I just thought if anybody is interested, you could go in that direction and read. Yeah, singularity. Yes, Shiva, you're right there. Okay, so underlying all these artificial intelligence systems is algorithms. Artificial intelligence are still algorithms. Okay, so it's only algorithms which will drive this human-like intelligence. Okay, so AI is an abstract concept. Okay, so AI is where we are and where we are going towards human-like intelligence, and there are specific terms for this. We call it as artificial general intelligence. Okay, so this singularity is called artificial general intelligence, where AGI is a superior form of, I think the other is called artificial specific intelligence, if I'm not wrong. When it reaches AGI, general intelligence is when it can do things like how human beings do. Okay, sort of sentient, sort of self-aware kind of state. Okay, but artificial specific intelligence, or sorry, not specific intelligence, ANI, artificial narrow intelligence. Okay, artificial narrow intelligence is when it's driven by a set of primitive algorithms. It can only do a certain set of tasks. Okay, it can only do one thing at a time. It cannot do everything. Okay, so it's a tool that will do it's specific to a particular task. That's what we have now. Computers are doing specific tasks and a wide range of tasks, but it's narrow. It's one at a time. It does only certain mathematical problems, certain predictions, certain pattern recognitions, etc. So we're currently in artificial a narrow intelligence. This is more of an abstract. This is it's more of the aspirational where it would go towards. Okay. Okay. So that's enough of artificial intelligence. So what is machine learning? Okay. Machine learning is what we have today. Okay. It's a set of algorithms which finds relationship between variables. Okay. So all your decision trees, associative rule mining, clustering algorithms, all that is called as machine learning. Okay, so machine learning is where primarily data science is. If you call what is data science is largely machine learning. Okay, so what is machine learning? Machine learning is a set of algorithms which performs a specific task. What is different from a typical software and machine learning is that the machine learning starts off with an algorithm, okay, with a skeletal algorithm. And when you feed data into this algorithm, when you feed data into that algorithm, the algorithm learns from the data. You don't have to do much. You don't have to say that 10 times price minus 3 times cost is profit. You don't have to say that. Okay. If it's a linear regression algorithm, 10 and 3 are figured by the algorithm. Okay, so the patterns are recognized by the algorithm. What happens in a typical software is you need to feed everything. Okay, so your Tally software, the codes will exactly tell you which accounts to go, what to minus, subtract, add to get the result. Okay, so your accounting algorithm is a specific algorithm which has to be coded in a particular manner. In a machine learning algorithm, you have a skeletal mathematical base, okay, onto which you throw data. The algorithm is looking for patterns, and then it will arrive at the weights which are necessary. What features add to what weight? How many bedrooms? How many bathrooms? Whether a lawn exists or not? Our distance from the city center is equal to the price. Okay, so these weights are figured by the algorithm. And then if you put a new data into it, saying that here is a new house which has 4 bedrooms, 3 bathrooms, and a lawn, and it's 1 kilometer from the city center, the algorithm is supposedly will give the result. Okay, the weights are not decided by you. The weights are decided by the data that you feed to that algorithm. Okay, so we have, like I said, around 100 plus algorithm, of which if you know like 10 algorithms properly, it's more than sufficient. Okay, what you need to know is, I think, more like an application, which algorithm fits where, what is the problem in hand, which algorithms would be best suited to get the solutions. And data scientists most often, it's not like they know perfectly. So what we do is, any data is there, we throw in multiple algorithms and we take an average of several results. Okay, so let's keep it simple here. Artificial intelligence is a concept for computers to mimic human intelligence. Machine learning is here and now. It's what it refers to all the set of algorithms that are there out there, which helps us find patterns inside data. Okay, so that is machine learning. Many algorithms. You are a data scientist if you know like 80% of the or not 80%, like the main algorithm, 25-30 algorithms, if you know, and you substantially know the math behind it, then you are a data scientist. If you 10, 12 algorithms, you could start thinking in those lines. Okay, thinking of applying these algorithms to your the task in hand. You could communicate with the data scientist much better. Okay, and then you have something called as deep learning. So deep learning is a subset of machine learning. You could call it as an extension of machine learning. Okay, so deep learning begins where machine learning sort of ends. It's also a set of algorithms, but these algorithms are a little unique in the sense that they try to mimic the functioning of the human brain. Okay, so so it's a mimicking the function. Okay, so it's not exactly like there is a human brain inside the computer or anything. These are algorithms. It's just that the structure of the algorithm tends to mimic human brain. So basically, there are things like neurons and dendrites, etc., which is how the brain sort of receives stimuli from the external environment, and it passes those stimuli to other neurons inside. Okay, and these neurons will process the information. For example, I'm hearing some sound from outside, but I'm also listening to any participants who are going to speak. If I'm going to hear some sound from the window from outside, I'm going to ignore that sound. So there are a set of weights that the neuron gives to certain features, certain sounds. Okay, and certain weight is given, a higher weight is given to a certain other stimuli. Okay, like for example, if a participant is speaking. So this neuron is like it's a mathematical function basically, which is able to combine these information from outside, and then it passes on this to other neurons if necessary, or it could be a reaction like the human body. It could react in a particular way. Okay, so in that sense, this a set of scientists decided that the best way to structure algorithms is to sort of mimic the human brain instead of doing it like a recipe machine learning algorithm. Okay, it's like a recipe step by step, do this, and then use certain statistical models and mathematical models, etc. Instead of that, do a very simple weighting of inputs. Okay, you're getting inputs, you weight it, then you can apply a mathematical function here. Okay, so that's called an activation function. It's not necessary to know so much at this level, but just think of deep learning as an evolved version of machine learning, and it seems to do better than machine learning with very large data sets, very complex data sets, and actually it's easier than machine learning. Okay, as a student of data science, deep learning is to know deep, because there is not much you can do in deep learning. The only thing you do is the number of neurons you can increase. You can play around with the activation function and all. Okay, this is sufficient for now. What is AI? What is ML? So if you look here, I have put artificial intelligence in the outside. That's the superset, and then you have machine learning, and then deep learning as a specialization of within machine. Okay, if you read some books, probably authors might disagree. They might put deep learning outside, say that this is a totally different way of looking at things. That's there's no uniform consensus on these sort of things. Any questions at this point?
Hi, one quick question.
Yeah, sure.
Yeah, just if you can go back to the previous slide.
Yeah.
Yeah, just, I mean, from a basic understanding point of view, which is a subset here and which is the main one? So everything falls under the umbrella of AI, or do we have to see it as, different groups or different applications or whatever, different purpose-driven applications?
Yeah. So everything falls under AI. You're right. Everything falls under AI. Okay. So the you could write AI outside. So the whole thing is artificial intelligence. Like I said, we are going from a primitive calculator to singularity. Okay, like the point where machines will exceed human intelligence. Okay, so that's the whole journey. It's an abstract concept. Okay, nobody knows where we are at this point. Whether we are 50 years away from singularity, all that we don't know. All we know is we are able to train machines using certain algorithms to solve problems for us. At this moment, it's narrow intelligence. That means you give data, it solves patterns and gives it back to you. Or it can do certain robotic actions. It can make a car probably. but it can't do everything that a human being does. Okay, so we are at ANI. So you could think of that as the abstract field. The overall field is called artificial intelligence. Now, machine learning has got a specific reference, at least. So when you search machine learning on Google, or if you look at machine learning books, or you talk to a data scientist about machine learning, it refers to like the things that I have said in the previous slide, the specific algorithms, decision trees, linear regression. So machine learning are nothing but algorithms which deciphers patterns in data. Now, deep learning is the only place where people have a disagreement as to what it is, but this is one view that deep learning is a type of machine learning, because deep learning still does the same thing, which is to recognize patterns. It's just that the design of the algorithm mimics the human brain. Okay, so it takes in input and then it processes it. It has an activation function. Then it sends it to another of neurons. I will show you the demonstration of deep learning algorithm, how it looks. But it's yeah.
So what then is the deal breaker? I mean, slightly off tangent question. What then is the deal breaker to, when you say point of singularity and then you don't know whether it is going to be machines taken over or humans still controlling machines? What differentiates us, right? I mean, our intuition and our ability to see patterns still exist. Probably the way I see it, it could be a naive thought, but the way I see it is the machine today can process large amounts of data and correlate it. But that's what we also do, right, with our natural intelligence. So what's the deal breaker?
Yeah. So, so machines are not. So this is a very philosophical concept. What is humans and what is machines? So it could be things like being sentient, being self-aware. Can it do a range of tasks? For example, machines can't even today. Machines can't even do what a 2-year-old does very naturally. Okay, so it can distinguish between. Yeah.
Why then should we be scared of, or I mean, not scared, not the right term to use. Why then should I be apprehensive of what's beyond point of singularity?
Yeah, so that is something. It's a different debate. Why should we be scared? So basically, these guys have their views. I think the fear is that a few set of individuals, just like how we have data controlled by the Googles and Microsofts. Again, you have corporations which will control. So that is a bad thing. And then if it takes over a nuclear reactor and things like that, then it becomes very dangerous.
Okay, got it. Right, sure.
I have one question.
Yeah.
Deepak here again. So you explained very beautifully that machine learning is a set of algorithms that finds relationships between a set of variables. And then you said that the starting point is a skeleton mathematical base, which you keep on, which it keeps on learning by itself when you give data. Now that you've got it set and you're very happy with it, so now you start in a production mode and you use that algorithm, but it will again keep on learning from the data. So you don't want that, no?
Yeah, so I will come to the next slide where we discuss the steps in data science, steps in machine learning, applying machine learning. So just wait for that slide. If your doubt still persists, then I'll come back to it. Okay. Okay, so so remind me if I don't show the deep learning version of machine learning algorithms. I don't want to show it now because the right order would be to discuss machine learning and then go to deep learning if time was. Let me go to the next slide. Okay, so broadly, what are the types of machine learning algorithms? Okay. So machine learning algorithms, like repeating, it's skeletal models, mathematical steps, which will help us find patterns, okay, which will help us recognize patterns. Okay, so a lot of times when you have data, so this is the Y column. When you have data, you don't know what is the relationship between these variables. If it is one-to-one, it's easy to find, like number of bedrooms and house price. You can find out, like house price is 100, 2 is 200, etc. It's goes in a certain linear fashion. But when you throw in more data, more columns, basically, okay, more columns, then it becomes a little difficult. I mean, definitely it becomes very hard to when you have 25, 30, 50, 100 columns, and then you have one output, which could be, like I said, ROI, customer retention, whether it's a fraud or not a fraud, etc. It becomes very difficult to say which combination of columns leads to a particular output. Okay, leads to a particular buy value. Okay. So that's where machine learning algorithms are very fast at understanding these patterns. Okay, so you throw this data into a machine learning algorithm and ask it to decipher the weights for each column, or what is a pattern. Okay, when we say pattern, it's nothing but weights. Okay, okay. So do you have to take this column at all? Maybe this column is irrelevant. Then the half of this column, 10% of this column, 5% of this column, and then add them up together, and then you get the result. So it's going from X to Y. Okay. So this X is called the independent variable. Okay. Some of you would have read in statistics what is independent and dependent. We use the same similar terminologies. There are other terminologies also. Okay. Okay, I'm just suddenly not remembering, but I'll come back to this response variable and input variable, and you could also say input output. Okay, or X variable and Y variable. Okay, universally, if you just say X and Y, people across the globe will understand. Statisticians understand this independent, dependent. Okay, input output. Okay, so
features and labels.
Okay, features. Good. Thanks. Features and labels. Yeah. Features and labels. Good. Okay, so we will come before we dive into what weights to give, etc. We have to classify all machine learning algorithms into certain buckets, so that when we start applying machine learning algorithm, it becomes easy to figure out which bucket to go and look at. Okay, which class of machine learning algorithms. So basically, there are largely two types of machine learning algorithms. One is called the supervised machine learning algorithm, and then there's something called as the unsupervised machine learning algorithm. Okay, supervised. So it all depends on the why we say what is it depending on. It depends on the type of data that we have. Okay, so remember there is X and Y. Okay, we refer to X to all these columns. Okay, all these columns put together is called as X. The last column is Y. So Y is always one column. Y is always one column. It's the output, but the input or the features will be one or many. Okay, so it's represented by capital X and capital Y, or sometimes small y, but capital X. Okay, so what we say is it requires the knowledge of both the outcome variable. Okay, outcome variable. So this label. Okay, so another name is outcome variable or the dependent variable. Okay, or the dependent variable, and the features. Okay? As one of you rightly reminded me, it's and the features, which is also called as the independent variable or the input variable. Okay, so this is referring to the data set. Okay, if you have this sort of data set where you have X, that means you have house price, which is the Y, and then you have X, which is number of bedrooms, square foot, lawn or not, distance from city center, all these X data you have, and then you have the house price, then you can use supervised machine learning algorithms. Okay, so the way supervised in the sense that the learning is happening under your supervision. Your supervision means you have given this pattern, you are given this output. See, basically it's a question and answer, both are given. All that the algorithm needs to do is find out the weights for each of these columns. Okay, so this is called supervised machine learning algorithms. So what the algorithm does, it learns. Okay, now this word learning is used. Okay, machine learning we say. Learning means it's basically a mathematical task. It estimates the values of the model parameters. Okay, parameters are called the weights. Okay, so how much is column 1? How much is column 2? How much is column 3? 5%, 10%. What weight to give to each column? Okay, which is usually a function. Okay, so the algorithm learns the model weights, but then we also need to know, now this goes into the crux of statistics and mathematics behind how does the algorithm work. Like someone was asking before, do we need to know how this algorithm figures out these weights? Okay, I would say it's not required if you are not a data scientist. Okay? It's but if you are a data scientist, you would be tested on your knowledge of the math stats behind that algorithm, how each one works, what's the difference between this and that. So there's something called as a loss function. Okay, so it's an iterative process. Okay, there is no magical way in which this machine learning. Uh, it's not like instantly the computer will figure out what is the thing. It does an iteration. What it does is it throws random weights initially. Okay, it throws random numbers and say that let me try out these numbers and figure out what is the predicted price. It just calculates predicted price. It'll be all nonsensical. Okay, so it will calculate a hat. Okay, it will calculate, okay, 350. It'll be a nonsensical calculation. But then what it does is it calculates something called as a loss. Loss in the sense how much I am off the target. Okay, how much I'm away from the target. And then what it does is it tries to minimize that loss. Okay. So I'll repeat, the way the machine learning figures out the weights is not in a very rigid, closed form of solution, although there are closed form solutions in machine learning algorithms. Typically, it uses an iterative random process. Okay, so it just throws some weights and it figures out what is the house price. Okay, it just randomly says, okay, some weights, and then it says, okay, 1-bedroom house costs 300, 2-bedroom costs only 50. Okay, now what is the loss here? The loss is it's off by 200 and 150, right? Okay, it's off by this. So the total, it's off by $350. Now it tries to minimize this loss. So again, it throws weights back and then it tries to minimize and then says, oh, it's become 300. Good. I'm approaching the solution. Okay. And then suddenly it says that 450. Oh, no. Hold on. Let me go back. 450 seems to be higher than my initial weight. Now let me just go down this path. Okay. So it takes next 200 and then it goes 50 and then 25. And then at some point it gets stuck. Okay, the algorithm keeps running, it gets stuck, saying that I'm not able to go below 25. I'm not able to go below 25. That point, it will stop. Okay, and this loss is typically revealed to the data scientist. Okay, so where the professional comes into place when he looks at this loss and says that, okay, the algorithm has sort of done its job. Beyond this, see what is the ideal loss for this? What is the best? What is the best situation for this? What is the best loss case? What is the best loss answer? Anyone? What should be the loss? Yeah, Manish, yes, you're right. Zero loss, right? 0. So you want your algorithm to predict exactly. So you don't want any difference between the house price that is there in the data and the house price that is predicted by the algorithm. You want it to be as close as possible. That it is that losses themselves are represented as a function. Okay, and the algorithm tries to minimize that function. So this goes into the weeds of how the machine learning algorithm actually works. Okay, this is something that if you're not, if you don't care too much about it, you just want to know how, which algorithms to apply, then you don't have to worry too much about this part. Okay, so because this is, there will be some loss functions to choose from in certain algorithms, but otherwise there'll be a default loss function to minimize, and the algorithm will do its job, and then you will get the model. Okay, so when you say a model, somebody was asking, where does this stop? Okay, where does it stop? What if it goes on? There are cases where it will run for a long time, so a data scientist would know where to stop it. Okay, so you can specify the number of iterations. Don't go beyond this. You can give a definite value saying that this is the loss that is tolerable, etc. You can fine tune. Whatever you get at the end is called a model. So basically, it will be like house price is equal to 1.5 times number of bedrooms plus 3 times if there is a lawn or not, plus 1.2 times x3, which is the distance from a city. Maybe then it is minus, and things like that. Okay, so all these pluses and minus, the entire model will be given to you. The algorithm will run and give you this model as the output. So I have put too many things in it. I hope it's not confusing, but in this slide, what you need to take away is that machine learning algorithms are overall classified into supervised and unsupervised. It depends on what is the type of data you have. If you have both question and answer, if you have both X and Y, and you want to figure out the pattern, then you use supervised learning algorithms. Okay, so what are those supervised learning algorithms? You have something called linear regression. Okay, you have something called as a logistic regression. Okay, you have decision trees that we saw. Okay, you have a few other algorithms. Okay, I don't want to put too many names here. There is SVM, KNN. Okay, so you have certain set of algorithms which you use when you have both the question and answer at your. Any questions? Any questions at all? You can ask any question. Yeah. This because this is actually something that would be handled over few days if you are into a data science course. But we have less time, so I'm skipping over many things. I'm not fully aware which parts I skipped, but hopefully trying to simplify it. If anything is not clear, you please feel free to.
I think it's a great introduction to the world of AI. I think
Okay.
fair enough so far.
Thanks. Okay, thanks.
What is the
Okay.
name of the book the programmers read for knowing all the various algorithms?
Yeah, so see, this is a little everything is available on the internet. Okay, so there are no like right books. Some books are like presumes the knowledge of Python. Okay, so it's not ideal, but there are certain books which are goes by the name of data mining or data analytics. Try to go in that direction. Business analytics, data analytics. If you are going to start learning machine learning, I would recommend, I'll also show you in the next slide what is the ecosystem that forms this thing. You will need to know a little bit. I mean, you need to start off with Python and then certain tools in Python and then move to machine learning. Okay, I will cover the ecosystem in a while, and then you can ask me. Okay, I'm trying to go to the next slide. This is the next type of algorithms. We covered supervised machine learning algorithms. Then there's another set of algorithms called as unsupervised machine learning algorithms. What is unsupervised? In unsupervised, you have only the X. You don't have Y. There is no Y. There is no answer. There's no right, wrong answer. Okay. You just have features. You just have variables. Okay. For example, you would have, let's say, Flipkart is trying to analyze its customers. Okay, analyze its customer profile. It looks at all the customer data. It looks at Ashok age, so and so, last purchases, this item, so much value he has purchased in the last 12 months. Okay, the highest value purchase is he bought like a TV sometime back. That's the highest value purchase. What's the most frequently bought item, etc. It analyzes my data thoroughly. Okay, and then it goes to the next customer, and then it analyzes his or her buying pattern, demography, etc. Now the question is, it wants to give labels to this. Okay, but there is no prior label available. It's not like Ashok has, I have voluntarily said, hi, I'm a high premium customer, or I'm a budget customer, I'm a medium customer. We don't reveal things like that. We just go buy things, and then that data is captured. So this is a situation where we don't know what is the why. Okay, we would like to know what is the label, category A category customer, B category customer, C category. But unfortunately, no customer is saying that, hey, put me in A, put me in B. The algorithm will have to figure out the why. Okay, the algorithm will have to figure out the why, or you are interested in segmenting your customer database. Okay, so for this you use something called as unsupervised machine learning algorithm. So we don't have knowledge of the outcome variable. Okay, we don't have knowledge of the outcome variable in the data set. The algorithm must find possible values of the outcome variable. Okay, so algorithm will make an effort to find a label, suitable label for Ashok, for this customer. Okay, so this machine learning, this is called as unsupervised. Basically, there are some further it's categorized as clustering algorithms. Okay, so when you say clustering, it's again a set of algorithms. But typically unsupervised algorithms, when you say for a data scientist, it just means clustering algorithms. Okay, so they may not use the word unsupervised, but they will say clustering algorithms. Clustering means, what is a cluster? Like Nagar is a cluster. Okay, so you look at proximity of this is X. Okay, so this is X1, X2. Let's say these are two features, and then Ashok has some value here, and then let's say Anup has a value here. Now, with the knowledge of X1 and X2, you have to find the distance between Ashok and Anup, so two customers. Okay. For example, if this X1 and X2, let's say this is the dollar value of purchases, and let's say this is the category, okay, category of product, and let's say Anup is here, and let's say I have spent $120, and let's say Anup has spent $119, and his category is books. And lo and behold, my category is also books. His category is also. I'm trying to give a very simple example. So are we a cluster or not? Okay, we are obviously a cluster because we are buying the same category and our dollar spent is also the same. So it doesn't matter, like the names don't matter now. We are one cluster. Okay, but let's say Deepika, she is bought 500 and she has bought some other XYZ item. Does it make any sense to put her inside this cluster? It doesn't make any sense to put her inside this cluster. She probably belongs to another cluster. Okay, it doesn't matter what names you give to these clusters. Okay, that's up to the business development team to come up with innovative names for this. Like this XY, there might be some 100 different columns. Okay, like I said, purchase value till date, highest purchase, last 3 months purchase, and so on and so forth. You can keep giving all those information with city, etc. So across all these dimensions, it's going to measure sort of that goes into the math. How does this form clusters? Okay, it's purely a mathematical function. Okay, it puts it in a coordinate system and then tries to see where these customers are. So obviously these are together, these are together. So you have two clusters, A cluster and B cluster are premium, budget, etc. So this data scientist would do this sitting with the marketing business development team, come up with names, and then they could target these customers. Okay, because otherwise advertising dollar spent wrongly targeting this item to me or targeting these items to the next other customer may not be ideal. Okay, but if you target it correctly, then your advertising spend is makes sense. So that largely we call this as clustering algorithms. Okay, so there are some this thing. K means clustering. Okay, so for if at all you're speaking to a data scientist, you just said K means clustering, you would be very happy. Then DB scan is one more clustering algorithm. So there are a few more. Okay, maybe 5-6 algorithms are there within clustering. K means DB scan and one more I cover, but okay, anyway, forget. So these are the clustering algorithm. Then something called as principal component analysis. It's a mathematical, again, everything's mathematical algorithm, but here it is purely doing some other function. It's not a clustering algorithm. Okay, PCA, principal component analysis. Basically, if you have, let's say, X1, X2, X3, 3 features, okay, dollar spend, city, category, it's fine. But there are some data sets which can go into several million rows or a million columns. I'm saying million. Okay, so it could be 100,000 columns. Okay, or it could be 1 million columns of data. Just features, 1 million features possible. Okay, are you guys with me? That what I'm saying is this data set itself will have like 1 million features. Have you heard of any recent technology where they speak in terms of parameters? They say this technology has 1 billion parameters.
Chat GPT.
Exactly. So when you talk about this, all this Chat GPT is 3.5 whatever version that is there, and then the competitor says Bard is coming out with some other one, and then there's something else is in the works. They say 1 billion, 60 billion parameters. So when they say parameters, it's actually the columns. Okay, so it's actually the number of columns. Okay, so PCA is basically a technique to shrink the columns. Okay, it's basically a technique to shrink the data set without losing much information. Okay, PCA is to, you have a big data set, you want to shrink it you will lose some information, but 95% of the critical information is retained. Okay, it's a very matrix algebra technique. Okay, it's through matrix algebra. There are some methods like eigenvector, eigenvalue, which are a little bit more complex mathematical techniques, not to reduce the dimensionality of a data set. Okay, we call it as dimensionality reduction technique. Why do we need to do it? We need to do it because every time handling 1 billion column data set or a 1 million column data set, it's going to be extremely time consuming. Every time you load it and run it, etc. And running itself will take a lot of time. Running in the sense, making the model, the learning process itself will take a lot of time. So before I do clustering, I will apply PCA on the data set. Before I do clustering or linear regression or any of these other algorithms, I will apply PCA, which is to shrink the size of the data set. Okay? It's used there. So PCA on its own, it's not a very useful technique. It's not nothing that you'll get any insights out of it. It's not predicting anything. It's only a mathematical technique to reduce the size of a data. Imagine like an Excel table all the way to the end. You want to shrink the data. Okay. What technique you will use? You will use principal component analysis. It's a technique in linear algebra. Reduce the dimension. It's like a picture which is miniaturized, okay, but still it looks the same. The dimensions are reduced proportionally, but you get the beauty art of the picture, in fact. Okay, that is principal concept. So it's an intermediate step in number crunching, and it's an intermediate step in machine learning. Put PCA, convert the data into a smaller dimension. There will be some data leakage, some information leakage, but you're okay because what you save is tremendous amount of processing time and dollars. Okay, so that is PCA. All this come under this family called as unsupervised machine learning algorithm. What you need to know from this slide is what is unsupervised machine learning algorithm, where it is used. It's used in a data set where you have only the features. Okay, you have only the X values. You have only the variables. There are no answers. You're looking for answers. Okay, and typically it's used in some sort of grouping, segmentation. It's used in any sort of thing where you don't know the answer. Some population characteristics you're analyzing. Okay, you want to segment them. Okay, some disease thing you're analyzing, some cell biology you're analyzing. You can use this to understand which ones are similar. And the examples of these are K means K means, okay. K refers to the number of clusters that you want. Okay, so K is typically like 1 to 5. I mean, it's just an example. Okay, it could be 10 also, but typically it's less. Okay, because what will you do with 10 different customer segments? Typically 1, 2, 3. In that sense, there's a cost associated with having too many Ks, but K is typically like 1 to 5. That's the number of clusters. Okay, so like this AB. So this here K is equal to 2. Okay, means is, you know, statistics mean, right? Average. Okay, so basically there is something to do with the middle of this. Okay, middle average of this. It's basically trying to measure the distance. Okay, distance between the points and say that, hey, I like these 3 points are nearer to me, so they form a cluster. It's like you are in T Nagar. There must be some boundary to say that you are in T Nagar. Okay. If you are far away, then you can't say that you are in T Nagar. So that center of T Nagar has, that is the mean. Okay, so sometimes we call it as a centroid or the center. Okay, so that's what you have. You take two means, and then the algorithm will figure out this, which is the best spot. So these means are not, you're not giving these values. Okay, you are only telling that I want 2 clusters. This you have to give. You have to give this. This algorithm will not figure out. At least in the K means it will not figure. It will ask you, hey, how many clusters do you want? And then once you say 2, it will start throwing darts at this. Okay, that's why I'm using crude words like darts, trying to find out an optimum value of a mean from which the points are closer. Okay, so it's purely purely arithmetical, mathematical, that it's in a coordinate system. It tries to find out values that are data points. Okay, each is a data point, each is a customer that closest to this. Okay, so I know that's it's a lot going on today. Okay, so so basically K means something which you would discuss over 2 hours, basically. Okay, with the coding, with the codes and all. Any questions?
Yes, sir. You mentioned that you have to give the number of clusters. Now,
Yeah.
Because the whole thing about ML and all this is all about definition. So does it mean, is it hyperparameterization? You call it hyperparameterization when you give the number of clusters?
Yeah, it is parameter, hyperparameter. Yeah, you are right. It's something that you give an input to the algorithm. You drive the algorithm in a particular direction. You can call it as a hyperparameter. Okay. There are a little bit better situations where we can discuss hyperparameter, but for those who don't know, don't worry. It's just what is the input that you require the algorithm to run. Like basically, if it doesn't have this input, the algorithm can't efficiently find out. It can't run, right? So sometimes it's called as a hyperparameter, okay, or you just call it as an input for this model. Okay. Okay. Now, okay. So we have covered so far. Okay, we have half an hour more. Okay, so far we have covered what is data science, what is machine learning, what are the types of algorithms, what is supervised machine learning, the terminologies X, Y, dependent variable, independent variable. What are the different types of supervised algorithms that are available, and then what is unsupervised machine learning algorithm? We saw clustering, and then we saw this PC. Okay, now we'll see the overall business approach, how you implement data science project, or how do you implement data science? How do you implement these algorithms? Basically, you start with identifying a problem. Okay, problem opportunity for value creation. Okay, so it could be an internal audit thing. You want to detect fraud. Okay, so you want to detect some misstatements, some weaknesses, some errors in the system. Some transactions have erroneously been accounted. Whatever is that problem statement you detect, you frame that problem statement. Now, like I said, data science is not without data. You need data. Okay, so you have to identify the sources of data. Okay, primary, secondary, and then organizations create something called as a data lake. This is like a database which is a link to the organization. It's a giant repository where you can pull features or you can pull data as and when you like. So basically, it's a source of data. Okay, you need data. Okay, raw data. Before you pass it to the machine learning algorithm, you need data. And then we do something called pre-processing. Usually, large data set will have missing values, some incorrect data, which you have to apply some statistical techniques, some filtering techniques. You can use some visualization technique in order to see if there are some anomalous data. So this pre-processing is an important part. You could also generate derived variables. Okay, derived and the third column might be more relevant. Okay, so that's called a derived variable. It's also called as feature engineering. Okay, so suppose you have time and then you have distance traveled, then probably you can make a variable called speed. Okay, and then you can discard these two columns. You just keep one column, and probably this will have more information value than having these two separate columns. Okay, so you could have derived columns, and then you transform the data as necessary. Okay, and then once you do get your data set proper, you get a clean data set. Where you remove all NA values, missing values. You find some incorrect entries by some techniques. How do you find something is incorrect? Is something is entered wrong? Okay, like too many zeros, big value, and you just look at it. You do a dot plot and you see some figure is off the charts, and you know that it's an incorrect value. Of course, you have to use some other judgment also before you discard values. And then you can also do feature engineering, which is to cleverly combine some features in order to retain information or sometimes enhance that information value. Okay, and then this is something I'll come to it a little bit later. The data sets, divide the data set into training and validation. Okay, and this is also called as test data. Okay, it's also called test data. Basically, the model is trained. Okay, that is trained as in the learning. Okay, when you say training, yeah, it means learning. The model is learning from the training data. Okay, and then you see if the model works well on the test data. Okay, so test data is not your other like computer assisted CAT test data, where you send some data into the system and then see if it is working well. It's not that. Here, data is split. Okay, the data that at this stage, whatever data you have is split 80-20, typically 80-20 training. Training is nothing but learning. Okay, and this 20 is for testing. Okay, so once the model learns from the data, you don't instantly ship the model. You have some mechanism to test. It's like software testing, model working. It's sometimes what happens is the model will look very good with the training data. Okay, but you need a way to test. So this 20 is actually a blind data. Blind in the sense there is no leakage from here to here, as in it's split. It's split, and then the model sees, the algorithm sees only the 80%. Okay, so you give it housing data set of, let's say, Chennai housing data set. Okay, for example, Chennai housing data set you give. You have data of 500 houses, you make a model. And then you go out to test that model. You give 100 new houses. Let's say you give test data is from some other city, possible. Okay, or from the same city. But that test data is never revealed before, as in it's not leaked into the training. The model has no awareness of the test. It is completely fresh. It hits it on space fresh testing data. Usually, training data, on the training data, if you see how the model has performed, it will give like a 90% accuracy. As in, you feed the training data again to the model and say, hey, give me the result. Training data will obviously, the model will obviously perform very well. So you can't rely only on the training data to evaluate. So it's a form of evaluation. Okay, it's like you're reading a book for the exam. Okay, you're reading a book. You studied it thoroughly. You go to the exam. The questions are not exactly repeating from the end of the chapters. In the exam, they have a different way of asking these questions. Okay, and that really tests your knowledge. Okay, if it is the repeat of the study material, back of chapters questions, then you are just regurgitating, repeating whatever is there in the text. You really don't know if you have understood the concept. Okay, so that's what we are trying to do with the test data. We are evaluating whether our model has really learned the underlying pattern, or has it just this thing by randomly just assigned some value, got some weights, and that weights have no connection with the real world. Okay, so before you ship the model to the client, we always evaluate. Okay, and sometimes there is test data and then there's a validation data, and there are some other variations, but largely the principle is model is always blind tested with fresh. What do you do after testing? So if you get a 90% accuracy and against testing data, you get 60% accuracy. Okay, 60% only. There's a huge error. Then you don't ship this model. Then you go back and find out, investigate what went wrong. Okay, did you use the right algorithm? Is the data set pre-processed properly? Are features missing? Can you put more and can you engineer more features? And as somebody mentioned, are some hyperparameters out of tune? You have to change some parameters. So all those are specific things that a data scientist would come into the thing, and he know where to adjust the model in order to get in order to perform well against a future test. Okay, so we would try to bridge this gap. So if our training data accuracy is 80%, we'll at least try to see if the test data accuracy is 75%. You see, there is this gap is okay. Okay, but we don't want a big drop in the. There are no fixed values here. It all depends on the assignment. Some data science, some clients might demand a higher test accuracy. Some might be okay with it. Okay, so even a high test accuracy is no guarantee, because in future things might change, the relationships might change, loss might change, some things might have changed, and then incoming data predictions may not go smoothly. So that way it's not like an accurate thing. You try to build a model with a sufficiently high test accuracy. Build models, identify best model using model performance and the validation data. Build ML models in the sense that we try to build a couple of models, use a couple of different algorithms, and then see which is the best one. Okay, or we try to make an ensemble. Ensemble means a collection of models. Okay, collection of models and present it to the client. Okay, implement, decision, develop, wherever it takes you. So this is largely the steps. Okay, the step is the problem in hand. Okay, the data source, you need data. Okay, and then you pre-process, clean up the data, and then you split the data into training, testing. You build the models, identify the best performing model. Okay, so I was telling you previously what are the toolkits that is required to run this data science project. The primary thing where it all starts is the language, okay, programming language. You need to choose your programming language. So as you know, Python is the most popular one, okay? But there is another language called R. So R is a software. It's you can download it from the internet. It's free. Python is also free. Python is a programming language. R is a programming language, plus it comes in a package. Okay, R Studio it's called, comes in a package, so you get a nice little software interface, and you can start coding. You can start importing data. It's built.
Bye.
Okay, so then if you're going down our route, it's a different route. Okay, it's a different route. It's a faster route to data science. Okay, R, because R is friendly. It's a closed thing. It's there's a software called as R Studio. You can easily download it and start learning R language. You have to learn the language, and then you can start exploring the various machine learning algorithms, etc. inside R. If you go down Python road, you learn the programming language, and then there are some libraries that you need to learn. There's a library called Panda. Okay, and there's Panda is like Panda is equivalent of It doesn't look like Excel. Okay, it doesn't look like Excel, but I would say like just making a
time unte, you know, Max.
Please. Okay. So pandas is like is a tool to do mathematical calculations, etc. So pandas is actually a library. It's written on. It's written using Python. It can lose comparison with Excel to do formula calculations, manipulations, etc. Then you have NumPy. NumPy is again another package which is used to do calculations, array manipulations, etc. So you need to know pandas, NumPy. Seaborn is a visualization tool to draw charts, etc. Matplotlib is also a visualization. So once you get familiar with the Python libraries, then you come to another library called as scikit, okay, scientific kit. This is a library. It's also again written in Python, C, etc. This is where all the machine learning algorithms are residing. Okay, so you need to when you're working, you will have to import the scikit-learn and access all the machine learning. All the machine learning algorithms are inside the scikit-learn library. So Python, the programming language, then add on top of it, you need to learn pandas, NumPy. So all these are libraries. Okay, these libraries to understand, you need to know the base programming language. Okay, otherwise, if you directly come to this, it might be a bit confusing. And then finally, the machine learning algorithms, which is inside scikit, which is also Python written. Okay, so once you know Python, you will be able to read the documentation of scikit-learn and then figure out how to use this. Okay, now where is the playground for all this? The playground for all this is something called as the Jupyter Notebook. Okay, something called as the Jupyter Notebook. It's these. It's like a notebook where you can write the codes. Okay? So Python is the exe. It's a programming file, as in it is the program. Okay, so it's the interpreter. You don't open the interpreter and start typing. When you learn, you might be using, but eventually when you are doing application data science work, you will be working on a Jupyter notebook. Okay, so it's like a notebook. It's a software application. It's like a notebook with which will have cells like Excel, which cell in the sense not row column, just rows. Okay, and here you will write your code, which is Python code. But you will not be writing raw Python code. You will be writing a mix of with using pandas. You could write raw Python code also. Will run it. It's very efficient. You could write programs here. You could also write panda-based Python codes here. Okay, and your scikit-learn, everything happens in this Jupyter notebook. Okay, everything happens within this Jupyter notebook. Now this is on the desktop. Okay, it's the IDE, integrated development environment. It happens on your desktop, on your laptop. Okay, if you want to go online, there is something called as the Google Colab. Okay, Google Colab. That's an imitation of your Jupyter notebook. So if you know how to work on Jupyter notebook, you will know how to work on a Google Colab. Okay, everybody has it. Go to your Google.colab, then you will log in through your website and log in through your email ID, and then the Google Colab will open up. It's a free tool. Okay, now leaving this internet-based notebook aside, if you come through when you're learning, obviously, and even a lot of people use just their laptop and computers to run data science projects. Okay, so language, framework, one more framework which is for machine learning algorithm, a framework as in library, and then the playground where you will actually type codes. And then to put all this together, see, the question is now, how do I go and download each one of this? Okay, you could download it, but it's going to be a nightmare integrating all this together. Okay, you have to make your operating system understand that purpose. Okay, you have to make an environment, and then you have to put all this in that environment, and it has to sync and then work together. Python, pandas, NumPy, machine learning algorithms, your notebook, etc. So instead of doing all that, there is one company which has integrated all this and provides you as a single package. Everything is individually there, but it provides you a seamless working environment. That platform is called as the Anaconda package. Okay. So you see that animal names, quite a few. Python is snake, anaconda, and then you also see pandas. So just play on animal names. So Anaconda is a master package which houses all these packages. Okay, so it would look something like this. Okay, so Anaconda is this. Okay, you can see my screen, right? Anaconda Navigator. So you have all these different things, right? So many not required tools will be there. Okay, but this is the Jupyter notebook. Okay, so once you how did I get this? Basically, I have to install Anaconda. Okay, once you get this, it's a software. Okay, so it goes like this, and then you can open Jupyter notebook. So Jupyter notebook would look like this is the Windows Explorer for Jupyter notebook. Okay, so and then you could open a file. So I'm opening the Jupyter notebook file. Okay, so this is a particular code that we'll get into. So we'll see if we have time. So basically, all this, like I said, it's rows of cells. Okay, and there are codes here. Okay, so you have to basically work in this environment. So you'll import files, data files. All this will import, and then you can run your codes in Jupyter notebook. I just want to give you a feel. Otherwise, it should not look like very theoretical. Okay, so this that was your Jupyter notebook. Okay, so what are the lessons for internal audit now? Okay, see, I'm not going to give any magic solutions for internal audit. I want you to think from basic principles. Okay, what is a machine learning algorithms? What are the different types? What are the algorithms that are available? And how, what situations each one is used. So basically, like I said, the first thing is obviously you need to have training data. Okay, we are talking about supervised machine learning. We're talking about both algorithms. Let's take the example of supervised. Let's apply supervised machine learning algorithm. We can think of X and Y call data. Now we need the X and we need the Y. We need the training data. So the first thing is, where is the training data? Okay, so this has to be deliberately built. Okay, you might be having records of internal control, testing results, some compliance assessments, some audit findings. You have to go back and see previous records where you have done control testing or some substantive testing, some audit findings that's there. You collect all that data. You have your self-assessment questionnaires, your MIS systems, data from ERP, CRM, all that. You have to build your training data first. Now, how does that training data look? Yeah, this is a very crude as in a top level, high level view. It's not exactly I'm going to do an algorithm today. When I say X and Y, I'm looking at some transactions which are all X, okay? And then Y is whether fraud exists or not, right? So 0 is no fraud and 1 is a fraud. So this is an example of how a snapshot of a training data would look like. And you can have many features here. These are all the independent variables. Okay, so these are your independent variables. These are your X, right? Transaction ID can be ignored. It's just a nominal data. It doesn't have any information value. Okay. These are all your X variable. What is the answer? The result is this. Okay. This is your Y. Okay. So this is Y. Now the question is, how do you map a relationship map a relationship from X to Y. Right? So you have transaction amount, you have vendor category, you have what department, you have the approval level, what sort of approval, what sort of purchase is this. You have some flags already in place, suspicious vendor, some, some sort of thing. See, these are not written in stone, okay? This is just some random features that I made. Probably this doesn't make sense at all. The point is, overall, what I'm trying to say is you have some data, transaction data, and you have some column which has the answer, okay? This is based on past internal audit finding, okay? Now, when we go for audit, every time you would be opening the files and checking new transactions. Every time you're applying, you got to apply your mind. But what I'm saying is, in the past also you have done the same thing. So why not use those findings to and then ask the model to now go and check future transactions and see if you can predict. Okay, so there's a new transaction. $900 you bought office supply. Okay, admin is bought it, approval level is low, it's offline, suspicious vendor, okay, some data, okay. And then you ask the computer and you ask the machine learning algorithm to sort of predict this, okay. So how did it predict? First, data, split it into training and testing, send the data to model or the algorithm. Okay, so the algorithm, once the parameters are fixed or the weights are fixed, it becomes a model. A model is obviously tested, and then there is an iteration process. You go back, fix the model, etc. And then you have a model which say, let's say it has 80% accuracy, and the data scientists say, hey, this is the best I could do. You can use this. Okay. Now you can help the data scientist by firstly giving him good data, clean data, and then the data scientist can use his or her imagination and do some feature engineering, clean up this data, etc. And then use very good algorithms, good models. Okay, so he has to decide, should I use decision tree for this? Okay, a decision tree would essentially say, hey, this is a transaction less than 500. Okay, is it electronics? Okay, and then is it offline? Offline, yes. Is it ordered by admin? Yes, and then it will say those transactions will be fraud. Okay, or it will give a percentage here. It will not. It will say 3 out of 5. Okay, so it will weigh towards fraud. Out of 5 transactions, 3 is fraud. So this decision tree is like a structure. Okay? It's a structure. It's a skeleton structure. It's how the past data is. Okay, if it is less than $500, if it is electronics, if it is an offline purchase, if it is ordered by admin, then there's a high likelihood of fraud. You see what I'm saying? Don't try to map this. I'm not looking at the actual thing, but I'm giving you an example. Okay. So you will get a big decision tree with your data. Okay. And all you have to do is send new data to it. So you could send your new data and ask the decision tree to pick up which is fraud, which is not fraud, good data, good to go transaction. So this thing you can do decision, you can do something called as logistic regression. Okay. Some other algorithms are there as well, classification algorithm. There's something called as random forest. Random forest is like a group of decision trees. Instead of relying on one decision tree, using some changes in the parameters, you can come up with different decision trees. Okay, that we won't go that side. But the crux is you need training data in order to apply an algorithm, in order to learn the parameters and come up with a good model. And once you have this model, you can feed new data. You can feed new data, X data, and ask it to predict the Y. So the thing is, data science is about unearthing patterns in existing data. And if you have been doing audit for so many years and you have all those findings, why leave that of patterns unused? You're basically saying that there is value in that data. Let me extract that value, and then let me reduce my work burden. Okay, and then obviously these are predictions, and you could tailor your audit methodology around this. You could then substantively test certain transactions in this, and if you are comfortable with this sort of thing, then you could say that this is the. Sometimes this is the only way you could do things. Okay? This is the only way you could do things. For example, I have another concept which. Before I come to that, is this overall idea, is it okay?
Fine, sir.
Okay, okay. So think about all sorts of training data, where it could be fraud, it could be error, it could be some failure in the internal in the control systems, and then you it's all up to you. This is where you bring your experience. I don't do internal audit. It's been many years since I've done internal audit, but things
Sir,
have changed. A lot of audit techniques are there. Yeah.
It was really interesting. Just I would like to submit upon 2-3 scenarios where I feel the training data can be built for internal audit. There are 3 approaches which normally I undertake. Just as a data scientist, you may suggest. One is a generic way of doing a control testing, assessments over wide profiles, and then collecting the observations and seeing the patterns on various layers. This is one approach, sir, where I feel the training data can be easily built upon. The second is entirely dumping the core banking. I am from a banking scenario where the core banking solution has a defined set of parameters on which it is built, and we are trying to see its deviations and exemptions on product wise or by operational wise. The entire parameterization, I undertake a dump analysis sort of thing, where I see the framework what Ashok is trying to put upon seems to be most means relevant and deployable, derivable, and seems to be very interesting. And it can machine can do a lot of learning and give once we put the algorithms. I need to think which algorithm can do what. It's the sort of small understanding I visualize. Thank you, sir.
Yeah. Anyone wants to add anything? Okay. Thanks, Mr. Sridhar. So just one more thing is, you see this Y column. Okay, so this is your past findings, right? So this is something that you already put in efforts. Okay, so
exactly.
In efforts. Yeah. Now that effort should not go waste. It's the collective mind of several hours of qualified people who have found out this thing. What you're doing with data science is you're capturing that knowledge. Okay, you're capturing that knowledge. You are asking algorithms to figure out what combination of this leads to this. Okay, and that's what data science is about. It's about extracting value from data. It's about solving problems. One sidetrack thing is this sort of thing. You see, previously we talked about house prices, $100, $200. Okay, that's called as a regression. Okay, that's called as a regression task. Okay, where it is in amounts. So you're predicting sales. You're running a linear regression algorithm. You're saying that marketing expenses should be this much in the company. Let's say you're a statutory auditor. Marketing expenses should be this much, but you find something else. That's a regression task where it is dollar amounts. This sort of task is called as a. But here you see, you don't see amounts. You see labels. Somebody once said labels. You see 0 1s, binary. Okay, this is called as a classification task. Okay, classification task. So not only algorithms are classified as supervised and unsupervised. Within supervised, you have a regression task or a classification task. Are you classifying transactions as either this or that? Is it it's a fraud transaction? It's not a fraud transaction. So the fraud is coded as 1 and no fraud is coded as 0. So there are algorithms which does classifications. There are algorithms which does regression. So that also you just keep in mind. So all algorithms, supervised, unsupervised. Within supervised, you have a regression task and then classification. Unsupervised, you don't have the Y column only. So where is the question of regression and unclassification? Unsupervised is just clustering, that's all. Regression is specific dollar amounts. Okay. Classification is 0 or 1, binary. See, computers can't understand all these words. Okay. I'm speaking to the complete layman here, in case you understand that computers will not know what is admin sales. So there will be a pre-processing technique to convert this into numerical form. Okay, so we won't go into that. That's for the data scientists to figure out how to code office supplies, how to code travel. So that's a separate thing. But here you see values. Okay, so here you see binary values. Here you see dollar amount, but rest of the data you see it's all labels. Can computer understand? No, electronics and IT can different. We can't. So it has to be coded. It's a different process. It's part of the pre-processing that. How much AI is useful in data cleaning before? Yeah, so Sharon is asking how much AI is useful. See, this cleaning process, there are a lot of automated tools that are available. Okay, so it's making it easier, but still a data scientist has to manually sit and do a lot of cleaning. In fact, 80%, you won't believe 80% of the time a data scientist spends is in pre-processing. Okay, so only 20% is the interesting job. Data is always in a bad shape, pre-processing, converting all these text to values. That's called dummy variable, we call it. So all that takes a lot of time. Even though there are automated tools, we are still not there. Okay, where we can just take data and put it into. There's just one more small thing that I want to mention, and then we can close it. 8.5, another small concept, and then. Okay, so this I've already mentioned. Choice of algorithm. So you have to ask the task in hand, is it supervised or unsupervised? Is it labeled data or unlabeled data? Are you doing customer segmentation or are you detecting fraud? Okay, based on that, you go down. Then the next question is it regression or classification? The regression, as I said, is dollar amounts, estimating sales, estimating marketing expenses, well, estimating house prices. Those are all regression tasks. Classification task is binary. Typically binary, it can have more classes as well, but think of it for now as fraud, no fraud. Customer will churn, he will remain. Okay, those sort of things. Okay, heart disease is there, no heart disease. Cancer is there, no cancer. So typical yes, no kind of things as classification. What algorithms are available, then you can always go back and see these are all set things. If it is classification, you have logistic regression, you can use decision trees, etc. Sidetrack one side. Anaconda purchase software, does it require survey? Yeah, so Anaconda is a free software, okay. But I think you have to check the RAM capacity on the site. I don't remember. I think you should have at least 8 GB RAM on the safe side. Okay? It's a little heavy software because it gives an entire load of data science related libraries, things that you'll never use in your life. Also, it gives. I got a Q&A. I'm just answering that. Okay. So Anaconda is a heavy software. So if you are downloading, be aware. Do not blame me that your system slowed down. Just download it on a free laptop somewhere. It gives you more than what is required. That's what I'm trying to tell. It comes with everything. Okay, if you're downloading, just read Google, read stuff before downloading anything. Do not download, like for example, Python, if you want to learn only Python, just download Python language. Maybe it will take for you 6 months to a year to understand Python. Then you download Anaconda. If you're saying that, oh no, I know stuff, I want Python, I want everything, then you download. Okay, thanks, Ravi sir. Thanks. Okay, logistic regression. You can use logistic. I've put some features of algorithms. Okay, logistic regression is simple. Okay, smaller data set. It's a simple mathematical algorithm. The math behind this is fairly simple. Linear. It's a linear algorithm, classification algorithm. There are decision trees. Decision trees are also simple algorithms. You can use it for smaller data set. Even larger data set, you would use something called as random forest. Okay, forest tree. Okay? A set of decision tree becomes a forest. Then there is something called as support vector machines. Okay? Support vector machines. Then there are neural networks. Neural networks, which is your deep learning. Okay. So those are the main things. Okay, these are the main algorithms. And one final thing that I want to say is, apart from all these classification, regression, etc., we have a set of algorithms which come under the family called natural language processing, NLP. Natural language processing, NLP. For example, if you're given a volume of text, okay, 1,000 pages of text, and you want to summarize it, just like chat GPT, right? You want to summarize it. So now that's not a classification or a regression task. That's more the algorithm, machine learning algorithm should have the same capability as a human has when he or she reads some text. Okay? For example, if I say food at that restaurant is horrible, okay, it means that I don't like that restaurant, I don't like that food. It's a negative sentiment. Okay, or I love the food at that restaurant, then I love the movie, then it means I like that movie. Sometimes people tend to speak in double negatives. Okay, food is not bad. Okay, so the sentiment is slightly lukewarm, right? So we wanted data scientists, they wanted an algorithm which would summarize text and give us the succinct version of it. Okay. Now this is pre-chat GPT days. Okay, this is let's say a few years, maybe a decade old algorithms. NLP has been a struggling field. Okay, it was not popular because there were a lot of, it was not perfect. Okay, today there's a big advancement in terms of chat GPT. There are newer algorithms which have come in, BERT, Transformer, and all that. These are all probabilistic models. It's able to read a text and probabilistically predict what should be the next word, so on and so forth. So it has a very intelligent way of reading and understanding text. For us, business use, we still need to, let's say in data science, we have something called sentiment analysis, where we want to, let's say, read website comments. Okay, we want to read website comments and quickly come to a conclusion whether the product is having a positive rating or a negative feedback. See, one thing is rating. You can always give 5, 4, 3, 2, 1 rating, and then you can always do a mathematical average of it and easily see that, okay, it's a good rating or a bad rating. But there are places where people write comments. Okay. Now, if you have 100,000 commentators who commented, each person has commented 4 to 5 lines. Now, who is going to sit and read that whole text? Okay, it becomes difficult for a human to read the whole text. You could do probably sampling, but there are some better methods now for text analysis, which is called as sentiment analysis. But there is even you can use classification algorithm called naive Bayes, etc. So, for example, you want to read some big, thick legal agreement. and then summarize it, or not a legal agreement summarizing, but let me say you want to take a dump of emails. Somebody mentioned dump of data. So you take a dump of emails and you're doing an investigation and you want to unearth some very off the track conversations, okay? Some suspicious conversations. You could do that. Okay, you could do that using text analysis, using NLP. I have a very a simple thing where let's say let- yeah, so I have something. This is an example. Okay, so this is a data dump of comments. Okay, comments of, let's say, some product. I think MacBook. Okay. So it's amazing. Battery lasts 10 to 12 hours, etc. And then I have finally a MacBook thing. Got it in Diwali. Best laptop under 10K. So on and so forth. Okay, I've been using a MacBook Pro user. Looks like largely positive. Some other reason for 1 star. It's see, there are spelling mistakes, defective piece, sound quality was not good. Started giving issues with battery from 4 months. To flicker, so on and on and on. People write in all sorts of ways. Okay, dot 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 dot. You don't know if it's a sentence ending or a beginning. Okay, so imagine the challenges for some algorithm to pass through all this and thing. But you have there are tools to do this sort of thing. Okay, called as sentiment analysis. Okay, so there are several things in this. It's not possible to cover everything, but there's a way to sort of calculate the sentiment score. We go through this text. There are ways to clean up this text. There are ready libraries that cleans up this text, parses these words, and then assigns sort of sentiment value. Okay, so this is a very crude early natural language processing technique. So I'm trying to go back to the principles, which is why I'm trying to use this, where we sort of find out what is the sentiment value, and then we say that let's say negative sentiment is here, and then the positive sentiment is comments are here. So we see the distribution. We could get also a sample score. Okay, but there is a base file where what is a good word and what is a bad word. Okay, so I would show that also to you. Let's say there is this. This is a very simple dictionary sort of thing, which will keep, which has about 2000 words in it. Okay, 2500 words in it. So so if I can't spell out some pronounce some words here, I can't read words here, some are very bad, like wrathful, wreck, wronged, wow. So wow is 4, whereas wreck is -2, worsens, worship, verse, wow with a double O is 4, etc. So they have human being span is like, I don't know, like 10,000 words or something. They have captured some 2000 words and they have given scores for it. Okay. So what this algorithm does is it will parse through this text and it will tabulate. It can go sentence by sentence and calculate the sentiment value, the score for it, and then it can give a cumulative score for this. What is the mean score? 0.93. It's just above positive. And the mean score is just above positive. That means that retailer has job to do. Basically, he has his task cut out. Okay, so there are it's very less time to go through that, but there are algorithms which does this sort of sentiment. There is named entity recognition. Okay, named entity recognition. Again, let me just switch back to this file. Named entity recognition is actually a very simple thing. It will, yeah, it's a easy way of picking out the nouns, verbs, adjectives, etc. Okay, so what there are, it will try to say, okay, which are the major words, like which is the adjective best. Okay, what is a proposition? Laptop is a proposition. Sometimes it will go wrong. Like for example, 60K, it says it's a noun, I'm not sure. Want is a verb. Accounting is a noun, software is a noun. So you could get a sense of all the major, you could distill out all the verbs, for example. Okay, you could distill out all the verbs. So this is one thing which is coming up, and a lot of new developments have taken place. What you see in ChatGPT is a very advanced version of this. There is something called as transformers and BERT, okay, BRT and transform. That's the probabilistic model of predicting the next word. Okay, one question presents a similar type of video as per my viewing pattern, particularly for example, viewing so thing to yeah. If all these recommendation algorithms, Sridhar ji, by YouTube and Netflix, they are all driven by algorithms. Nobody knows. It's not like one person is sitting behind and recommending you, but you are getting, basically, to use a mathematical term, you're getting vectorized in some dimension. Okay, somewhere Sridhar's liking has been marked here, there, and any other movie with a similar closer score, okay, like clustering, okay, which is coming close to that, will get pushed to you. And if you watch it beyond a certain time, you will get marked there, and then your feature will be updated. Okay, so it is definitely a thing. What is a transformer? So transformers are algorithms, basically, in the natural language programming field. They are basically mathematical algorithms to understand text. It does sentiment analysis, named entity recognition. It's able to probabilistically predict words. Okay. So it's an algorithm which is part of the NLP family, I would say. Okay. Transformers and BERT, but okay, these are all new advancements. Like I would think, like the ideal would be there would be like a ChatGPT kind of API for us, for let's say for auditors, where we will put legal agreements and all data, internal control processes, and then you would ask questions via chat, asking if for this transaction, what is the process? If this transaction is stuck at this level, what is the next thing to do, etc. So an interactive chat interface would be the next thing that I would imagine that some of the consulting firms would be working on. Okay, at the end of the day, these tools should help the person who is doing the real job. Okay, so if you could have a chat GPT for audit, where you could dump the internal audit system description, and then you could ask questions how this works and how that works. Okay, we are running out of time, so let's close it here. Any questions?
Thanks, Ashok sir, for a very insightful session. I request Deepika to share a vote of thanks. Deepika, you're there?
Yeah, I'm there.
Thank you.
I think it was a very excellent session, sir, and the time allotted was very less, I think. You have so much content and you were able to relate with the audience very well with very lucid examples, and I think all of them are going with, you started by saying like, I'm not going to talk jargons, but I'm going to say all our participants are going to go back with a lot of jargons, which they understand better now from all the Python libraries and machine learning algorithms, etc. So very happy that you were able to spend time with us today. Looking forward for more sessions. If no further questions, I think we can call it a day and close. Looking forward to see you in future IEA sessions also, sir. Thank you very much.
Sure. Thanks, Deepika. To all the participants, I think the level of understanding has been very good. I had come with a different expectation, but I think my expectations are exceeded. So great audience, good questions, very relevant.
Yeah.
Okay, looking forward to connecting the next session. Yeah.
Yes, sir.
Thank you so
Sure,
much.
sure, sir. Thank you very much, sir. Thank you. Good
Thank you
night.
so
everyone.
much, sir. Good night.
Thank you. Bye. Good night.